Many of the calculations you perform in MATLAB will use single values. However, there will be times when you want to define a range of values, such as the odd numbers from 11 to 19 or the powers of 10. In this movie, I will show you how to create those ranges in your script. I have opened a new workspace and command window in MATLAB, and let's say, in the command window, that I want to assign a range of values from 3 to 7, incremented by 1, to the variable a. To do that, I will type a 3, which is the starting value, then a colon, and a 7, which is the final value. And when I press enter, you see I get 3, 4, 5, 6, and 7. If you don't put in a step value, MATLAB assumes that it should be 1. If you do want to add a step value, you can add that to your range assignment. So I'll type b equal, and then I'll start again at the number 3, followed by a colon, and here the step value will be 3, followed by another colon, and then the maximum of 15. And when I press enter, I get 3, 6, 9, 12, and 15, 3 incremented by 3 until we reach the maximum value of 15. If the maximum value that you put into your assignment, that is your range definition, can't be reached, then MATLAB will go as far as it can. So if I type c equals 3, colon 3, colon 14, then the last number that I see should be 12. And that's because 15 is larger than 14, and MATLAB therefore stops at 12. The step value can also be negative, so if I have a variable named d, type equal, I'd start at 20, then a colon, and minus 4, colon 4. So now we'll go from 20 to 4 in steps of minus 4. So I get 20, 16, 12, 8, and 4. One other way to define a linear space of values is to use the linspace keyword. So let's say that I have a variable named lins, L-I-N-S, then equal, and I want to go from 7 to 35 and have 5 values. So for that, I would have linspace, which is the keyword to use, in the left parentheses, and then the first value will be 7, comma, then the last value would be 35, comma, and I want to have 5 values in that range. So I'll type a 5 and a right parentheses and enter, and I get 7, 14, 21, 28, and 35. You can do the same thing with logarithmic values, which go up by powers of 10. So if I have a variable named logsp, and then equal, I would use the log space keyword, then the left parentheses, and here I will start at 1, then a comma, and then 5, and 5. So this command will give me the first 5 powers of 10. So when I press enter, I get 10, 100, 1,000, 10,000, and 100,000. One final thing to note is that you can concatenate or combine two sequences into a single one using brackets. So I have sequence B, which is 3 through 15, and D, which is 20 through 4, again incremented in steps of minus 4. So if I assign those two to the variable named E, then equal, I would use a left square bracket, B, which is the first variable, then D, which is the second, and a right square bracket to close out, and enter. And you see that MATLAB has combined or concatenated those two ranges into a single variable. Hopefully, these shortcuts will let you create the data that you need more quickly and efficiently. Elsewhere in this course, I showed you how to create ranges or sequences of numbers that followed a pattern. Many applications rely on random numbers, so in this movie, I will show you how to generate them using a variety of techniques. I am in a new command window within MATLAB, and if I want to generate a random decimal number between 0 and 1, then I can just type rand, R-A-N-D, and enter, and I get a value of 0.7112. If I were to type it again, I would get a different value. You can also generate uniformly distributed integers using the rand_i keyword. So if I type rand_i, then a left parentheses, I can define the range in which the integer will fall. So I have a left square bracket, then 1 is my minimum, 100 as the maximum, then a right square bracket to close that definition, and a right parentheses to close out the argument list, and enter, and I get an answer of 12. And if I were to type it again, rand I, left parentheses, left square bracket, 100, close out the square brackets and parentheses and enter, and I get 30. Those numbers are uniformly distributed within the range from 1 to 100, and that means that each value is equally likely to appear. If you want to generate random numbers with a normal distribution, that is with a mean, in this case of 0, and a standard deviation of 1, then you can use rand n. So I'll type rand n and enter, and I get a value of minus 0.5078. And if I were to type it again, I would get minus 0.3206. One more time just to see if I can get a positive number, and I do. Of course, we're working with a computer system, and that means that these random numbers aren't actually random. They are generated by an algorithm that is based on a seed value. So if you want to set the seed for your random number generator, you can use the RNG keyword followed by the seed value in parentheses. So let's say that I type RNG, and the seed value will be 15, and enter. I don't get any output because I was just generating a new number. Then I'll type rand and enter, and I get 0.8488. And if I type RNG 15 again, that resets the seed to 15. And if I type rand one more time, then I get exactly the same value. And just to show that things will change, I'll type rand one more time, and I get a different answer. You might wonder why you would want to set the seed for a random number generator. And the reason is that you can replicate a run, for example, of a simulation that occurred with that particular value. If you are creating a simulation or any kind of a random process, then if you find, based on a particular seed value, that you get an interesting or unexpected result, then you can write down the seed value and be able to recall that run of the simulation to demonstrate what could possibly happen within the scenario that you created. Two other ways that you can affect the random number generator's algorithm are to shuffle the seed value. And what that will do is pick a new seed based on the system clock. And you won't be able to see this. It will just reset within the system. So for that, you type RNG and then shuffle. And that's shuffle within single quotes, right parentheses, and enter. And again, there's no visible change, but the algorithm has been moved to a different seed value. And if you want to restore the default characteristics, you can type RNG, then the single quotes default, right parentheses, and enter, and you're back to the normal behavior. In MATLAB, a lot of your data will be stored in vectors and matrices, but those numbers are not just abstract concepts. They often represent factors in an equation that reflects the results of a business process or engineering model. If you want to change all of the values in a vector or matrix by a specific factor, either through addition, subtraction, multiplication, or division, you can do so quickly. You can also perform element-wise operations where you work with corresponding values in vectors or matrices that are the same shape. I'm in a new command window in MATLAB, and let's say that I want to define a vector values that are the numbers 1 through 5. So I will create a variable called VEC1 equals, and then I'll define the range within square brackets as 1:5, and close the square brackets and enter, and I get the values of 1 through 5 in a horizontal vector. If I want to add 3 to each of those values, then I can use the plus sign for addition. So I'll create a new variable, vector2, equal, and it will be vector1, VEC1, plus 3, and enter. And you can see that vector2 now contains each of the values from vector1 plus 3. If I add vector1 to vector2, then I should see the element-wise addition for each of the elements. So if I do VEC1 plus VEC2, and I could do this in either order because addition is commutative, and enter, and I get 5, 7, 9, 11, and 13. The same considerations are true of matrices. So if I define MAT1 equal, and then within square brackets, I'll have 14 colon 18. So I will have 5 values, 14, 15, 16, 17, and 18. Then a semicolon to indicate a new row, and then 21 colon 25. Right square bracket to close and enter, and there is matrix 1. Now let's say that matrix 2, MAT2, is equal to MAT1 minus 8. So I'm subtracting 8 from each of the elements within matrix 1, and enter, and there's the value. So instead of 14, 15, and 16, I start out in the first row with 6, 7, and 8. Adding the two matrices on an element-wise basis would be MAT1 plus MAT2, and enter. There I get the addition. 14 plus 6 is 20, and you can verify the others if you like. If I want to multiply the corresponding elements of two matrices together, then I can do that, but I don't use the asterisk, which is what you normally use. Instead, I use dot asterisk. So I'll start by typing MAT1, and then a period, and then an asterisk, and the period asterisk is used for dot multiplication, or element-wise multiplication, and then MAT2. And the first element of matrix 1 is 14, and then in matrix 2 it's 6. So 6 times 14 is 84, and that is what I should see at the top left when I multiply these two together, element-wise. So I'll press enter, and the first value is in fact 84. Just to show you what would happen if I were to try to use the asterisk to multiply matrix 1 and matrix 2, so I'll do MAT1 times MAT2, and I will get an error. And the reason that I received an error is because I'm trying to do matrix multiplication. And when you do matrix multiplication, you have to have certain characteristics for the two matrices and how they compare to each other, and in this case, that is not true. But if you want to perform any of these element-wise operations, you can do so using the techniques that I demonstrated in this movie. Matrix multiplication is one of the most useful skills that you have in linear algebra, and therefore in MATLAB. I'd like to start by describing a special case, which is vector-vector multiplication. A row vector has a single row and one or more columns. So here you see I have a 1 by 3, that's one row by 3 column vector. And again, this is just a matrix that has a single row. You can multiply that vector by another vector, but it has to be of an appropriate shape. And in this case, that means that it has 3 rows and 1 column. So if you multiply these together, you get a result that is 1 by 1, that is a single unit. So the question is, why does this work this way? Well, one of the rules of matrix multiplication is that the columns of the first vector, that is the number of them, must match the number of rows in the second vector. So you can see here that I have a 1 by 3 and a 3 by 1. When you write the measurements of a vector out like this, you can see that the interior numbers match. So we have 3 and 3. And you will get a result of the number of rows from the first item and the number of columns from the second. So here we have 1 row and 1 column, and that gives you a 1 by 1 result. Matrix multiplication is similar. So here I have a 2 by 3 matrix and a 3 by 1. And as we saw before, because we have the same number of columns in matrix 1 as we have rows in matrix 2, we can multiply them together. So here we get a result that is 2 by 1, which is the number of rows from the first matrix and the number of columns from the second. Here's how to do it wrong. In fact, you won't be able to do it at all. If you try to multiply two matrices, and here I have a matrix with 1 column, and I'm trying to multiply it by another matrix that has 2 rows, the one and the 2 won't match up, and that means that you get an error. So always remember, matrix multiplication is not commutative. The order of the matrices and their measurements matters. Matrix multiplication is one of the most useful techniques in linear algebra. In this movie, I will show you how to do it in MATLAB. I've created a new blank command window, and I can start by defining a couple of vectors that I will use in matrix multiplication. And again, a vector is a special case of a matrix where I have either one row or one column. So I'll start by defining a row vector. I'll call it v underscore row equals, and then in square brackets, I'll define the terms. So I'll have 1, then a comma, 3, comma, 5, comma, 7, and right square bracket to close it, and enter. And there I have my row. And now I will create a column vector. So that will be v underscore col. And these are just variable names. They're not mandatory. You can call them whatever you like. And within square brackets, I'll type a 2. And then I need to go to a new row because we are creating a column with a single item within each row. So I'll have a 2, 4, semicolon, 6, semicolon, and 8. Right square bracket to close and enter. And there I see my column vector. In matrix multiplication, the number of columns in the first element must match the number of rows in the second element. So v row is a 1 row, 4 column matrix or vector, and then v col has 4 rows and only 1 column. So that means I can multiply them in either order. So I'll start by showing you v underscore row times v underscore col for column and enter. And the result appears as the number of rows in the first element and the number of columns in the second. Because I multiplied a 1 by 4 by a 4 by 1, then I get a 1 by 1 or a single number as the answer. If I were to multiply them in the opposite order, which is possible in this case, then I will get a 4 by 4. So I will do v underscore col times v underscore row and enter, and I get a 4 by 4 matrix. The same considerations are true if I want to multiply two matrices together. So I will define matrix 1, mat1 equals, then left square bracket 1, comma 4, comma 8, then a semicolon to indicate I'm moving to the next row, 16, comma 32, comma 64, and a right square bracket. So when I press enter, you can see that I have a 2 by 3 matrix, 2 rows and 3 columns. And matrix 2, I will create as a 3 by 2, so 3 rows and 2 columns. So mat2 equals, left square bracket 11, comma 9, then a semicolon to indicate we're moving to the next row, 7, comma 5, semicolon, and then 3, comma 1, and a right square bracket to close out. And enter, and I get a 3 by 2. And if you look over in the workspace, you can see that I have the sizes of these different elements listed. So I have matrix 1 is a 2 by 3, matrix 2 is a 3 by 2, and you can see the same thing for my column and row vectors. So if you have your workspace displayed and you don't remember the shape of a particular variable, you can go over to the variable list and find it there. I'll multiply matrix 1 and matrix 2 together. So I'll do matrix 1 times matrix 2. And because matrix 1 is a 2 by 3 and matrix 2 is 3 by 2, I should get a 2 by 2 matrix as my result. So I'll press enter, and there you see it. If I go in the other direction, multiply matrix 2 by matrix 1, which I can do because these shapes are compatible, then I should get a 3 by 3, because I'm multiplying something with 3 rows by something with 3 columns. So enter, and there I get the result. So those are the mechanics of matrix multiplication in MATLAB. You will find many uses for them as you build models within the program. Matrices and vectors can contain many types of values. In this movie, I will assume they contain meaningful numbers such as measurements from a business process. Using those values, we can calculate minimums, maximums, running totals, and other characteristics of your data. I'm in a blank MATLAB command window, and I need to define a vector variable to work with for this example. So I'll start by defining a variable called vector1, vec1 equals, and then after a left square bracket, I'll type 3, comma, 9, comma 2, comma 14, comma 8, and then 7. Close that with a right square bracket and enter, and there is my row vector. Min will find the minimum value from a vector. So I'll type min, then left parentheses, and the variable I want to use is the only one I have. So that's offered in autocomplete. So vec1, right parentheses, and enter, and the minimum value is 2. As you might guess, there is a max function that will find the largest value. So max, vec1, right parentheses, and enter, and I get the largest value of 14, which we can verify visually. And also 2 is the smallest value. Sum will add all the elements in a vector together. So I'll do sum, and then vec1. I'm enclosing vec1 in parentheses, enter, and the answer is 43. You can also multiply all the elements together and get a product of all of those numbers, and that is prod, P-R-O-D. Then left parentheses, vec1, right parentheses, and enter, and you get 42,336. Most of the time you won't use prod to get the product of all the elements of a vector when you're working with whole numbers, but it can be very useful for probabilities. So if you have a series of conditional probabilities, such as 0.5 times 0.5, then using prod to get the total product of all of those items can be very useful to find the total probability of a series of independent events happening. You can also get a running total by calculating the cumulative sum as you go along. The keyword for that is cum sum, then left parentheses, vector1, right parentheses, and enter. And you get the cumulative sum as you go along. So 3 plus 9 is 12, 12 plus 2 is 14, continuing on. Cumulative product does the same thing. So cum prod, P-R-O-D, left parentheses, vector1, right parentheses, and enter. And you get the cumulative product moving from left to right. And then the largest value so far, or smallest, can be displayed using cum max and cum min. So cum max, again at vector1. You see here, it's 3 to start because that's the only value. Then 9 is larger than 2, and 14 is the largest value overall, so it continues on. To find the minimum, use cum min, vector1, and there you see you start with 3, and then 2, which is the smallest value, so it continues. So that's how these commands work for a vector. If you apply them to a matrix, then the functions operate on each column. So I'll define a matrix called MAT1 equals, and then in square brackets, 15, comma 14, comma 8, so that's the first row, 1, comma 7, comma 4, second row, and then 6, comma 20, comma 9, followed by a right square bracket. So I have all 3 rows with 3 columns, enter, and there's the matrix. I won't go through all of the examples, I'll just do 2. So I'll start with min of matrix 1, right parentheses to close out, and enter, and I get the minimum value from each column. So those are 1, 7, and 4. Same thing for the running total, or a cumulative sum. So I'll do cum sum for matrix 1, have matrix 1 in parentheses, and enter, and you can see I get the cumulative sum for each of the columns in the matrix. 15 plus 1 is 16, plus 6 is 22, continuing on throughout each column in my matrix. Many advanced linear algebra calculations require transposing and inverting matrices. In this movie, I will show you how to do both of them, starting with some work in PowerPoint to demonstrate what is actually happening. When you transpose a matrix, the original rows become the columns in the transposed matrix. So here we have the original matrix A, and the rows have the values 1, 2, 3, and 4, 5, 6. When we transpose it to create A prime, then 1, 2, 3 becomes the first column, and 4, 5, 6 becomes the second column. So once again, we are going from a 3 by 2 matrix to a transposed matrix where the original columns become the rows. Finding the inverse of a matrix is a little more difficult. Let's say that you have a square matrix, A, as shown here, and you want to find the inverse. Well, this is what the inverse looks like, but it's not obvious what's going on. What's happening for the inverted matrix is that when you multiply A by the inverse of A, you get the identity matrix. And again, an identity matrix has the primary diagonal, top left to bottom right, all ones, and all the other values are 0. So with that introduction in place, let's switch over to MATLAB and see how it works in the program. In MATLAB, I have created a new blank command window, and I'll start by defining a matrix to use. So I'll call the variable matrix1, just MAT1, and then in square brackets, I'll create 2 rows of values. So 1 colon 5. So the first row contains the values 1, 2, 3, 4, and 5, and 6 colon 10, followed by right square bracket, and there we have our 2 by 5 matrix. To transpose it, which I will assign to the variable MAT2 and then equal, it will be the original variable, so MAT1, followed by a single quote. And that is the symbol for transposition. You might also hear it referred to as, for example, A prime, or in this case, MAT1 prime. Then enter, and there you can see that the first row is now the first column, and the same for the second row becoming the second column. Now let's take a look at the inverse of a matrix. And again, for a square matrix, its inverse produces the identity matrix when multiplied by the original. And that would look like, for a 4 by 4 square matrix, the identity matrix created using the I keyword, and enter. So you can see we have 1 all the way along the primary diagonal, and everything else is 0. Next, I'll define a matrix for which we want to find the inverse. So I'll do MAT3 equals, and then left square bracket 1, comma 5, comma 9, comma 14, semicolon to move to the next row, 3, comma 6, comma 9, comma 12, semicolon, 5, comma 10, comma 14, comma 7, semicolon again, 1, comma 0, comma 2, comma 5. All right, everything looks good, so I'll press enter, and there is the matrix. To find the inverse, you can use the INV keyword. So variable name matrix4 equals INV of, INV, I had an extra O at the end, left parentheses, and then MAT3. And enter. And there is the calculated inverse shown as decimal values. And just to verify that they do in fact generate an identity matrix, I'll do MAT3 times MAT4 and enter. And we get 1s all the way along the top left to bottom right primary diagonal, and everything else is a 0. Now, some of the other values are -0 or +0, and the reason that's the case is because the inverse was calculated numerically, and not all of the values are exactly 0, but they are close enough, at least within floating point decimal precision.